Okay, welcome students. Today's experiment number 2 in Chem 121 lab. I always start the lecture with questions to my students. What is the purpose of today's lab? And 95% of the time my students say it's to study density. Sadly, that's not true. The real purpose of today's lab is we're using density as a tool to measure a student's precision versus their accuracy. And so we're going to do special calculations, which I'll show in a minute, on doing precision and accuracy. Let's talk about density. So density is our tool to get to precision and accuracy. What is density? Well, you should already know and have covered it in lecture. The density is the mass of an object versus the volume of said object. And so simply put, we say density is m over v. So we do not have any method for directly recording density, but we do have methods for recording both mass and volume. And so in the 4 parts of today's lab, we'll go through techniques of collecting data for mass and also collecting data for volumes, many of which will have to be calculated. So in the first part 1, we're going to do metal rods and we're going to weigh the mass directly, and that will be demonstrated in the video later. So we will do a direct measurement of mass. That being said, when you're talking about precision on a scale, you always use the entirety of whatever is on the display of the scale so that you have the correct precision in your measurement. If you are in my class, your precision is counted double on the first labs, including this lab, so make sure you use the correct precision of all measuring devices. Now, the other part of the density is the volume. Since we're using these metal cylinders, and if you look at them, we have an example here, 2 metal cylinders. They look the same. They have about the same height. Looks like about the same diameter, but they have 2 totally completely different densities. The reason being is one of them is made out of aluminum and the other one is made out of iron, and I can tell by holding it which is which. Now, how do we obtain a volume of an object like this? The one way in which we're going to measure is using this device called a caliper. The caliper is going to allow us to measure the diameter of the cylinder in addition to its length. And a volume of a cylinder is calculated by calculating the area of the circle times the length of the cylinder. So area of a circle is pi r squared, and the length, we'll just call that the height. Now, trying to measure a radius is next to impossible, but measuring the diameter is much easier. So we just need to remember that radius and diameter are related by the radius being exactly half of the diameter. Okay, so to make a measurement using a caliper has 2 parts. It has what's called the fixed ruler, and then it has a sliding part. And as you slide it, you'll see that these lines move up and down the ruler. On a caliper, the important part of the measurement is where does the 0 line go. That gives us our certain digits. Now, you should have learned in your lecture that every marking on a measuring device are called certain digits. In between the markings are the uncertain digits. So we will use the 0 line to determine our certain digits, and then the nice thing about calipers is that they have a vernier scale, and there's 20 lines over here to allow us to obtain the uncertain digits. And so to measure, we will take this aluminum rod and we'll first demonstrate measuring the diameter. So as you clamp the caliper down, you notice that the 0 line landed somewhere between 12 and 13 millimeters. So that means our certain digit is 12 millimeters, 12 point something something. Now, The sliding veneer scale, there's actually 20 lines here, are set as this line is 0.00, that one's 0.05, this one's 0.10, 0.15, 0.20, 0.25, and so on. All we have to do now is we have to look carefully at how these lines match up with the ruler. Now I'm going to use the 0.10 line as an example. It lands in between two lines. So that does not do what's called a perfect match. We are looking for a line that does a perfect match. That one missed, that one missed, that one's close, that one's close. Ooh, this one is very close to doing a perfect match. It looks like the 0.75 goes perfectly straight across from the ruler to the veneer scale, and the 0.80 is very close as well. So these three seem to be making a perfect match, and again, now they start to miss again. So when making a measurement using a caliper, you want to choose which of these lines makes the perfect match for your uncertain digits. In this case, I'm going to use the 0.75. So my measurement would be 12.75 millimeters. And I'm going to write that down over here, that the diameter was 12.75 millimeters. Okay, we will now do the same thing for the length, also called the height, of this cylinder. So we squeeze the caliper, and now we're going to look, where does the zero line up? And if you look carefully, the zero line came between 50 and 51. Yep, it's just between there. We got to hold this steady so it doesn't move. So it's between 50 and 51. So we know our height is going to be 50 point something millimeters. Again, we have to go and look at the 20 lines and find the one that matches the best. Nope, nope, nope. 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 Ooh, this one's pretty close. That's the 0.90 and the 0.95. They're both relatively close to matching. Now, if by chance you end up choosing the 10 line, and we'll pretend that that's our measurement today, that this one lined up the best, then our measurement would be 10 would change this to 51.00 millimeters. Now, if it's the 0 one that lined up the best, it would have been 50.00 millimeters, but I'm going to pick this one just for demonstration. However, if I had picked one of these two, it would have been 50.95 millimeters. Now 50.95 or 51.00 are equally as precise, and either one would work well in your calculations for this particular metal cylinder. Okay. Now that concludes our demonstration on how to use a caliper. We are going to begin our density lab by choosing a metal rod. Today we're going to choose copper. So we're going to take 3 metal rods of copper, and we're going to record both mass and density, and volume. We're going to do volume 2 different ways, but we're going to do mass directly. So to record the mass, we gently place it, the cylinder on the pan. We wait for the number to stop and record this in our notebook. So your first mass of rod 1 should be as shown on display. We will do the same thing with rod 2 now. Just double check our 0. Place rod 2 on the scale. Okay, record the mass for rod number 2. And then we'll do this for rod number 3. Okay, record the mass for rod number 3. Okay, we've now recorded the masses for these 3 rods. We're now going to take measurements so we can calculate density, and we're going to do this calculate the volume, and we're going to do this 2 different ways. The first way is with this caliper, which we will demonstrated earlier. We need to make a measurement of, first we're going to do the diameter. Now the first measurement you need is the 0 line. Alright, I will help you with the first measurement. We first need to determine the 0 line, and our 0 line is between 12 and 13 millimeters. So we know that's our certain digits, that's 12 point something. To obtain our uncertain digits, we need to look at these 20 lines and find the one that matches nearly straight across. And the best one, in my opinion, is the 6.5 line or the 0.70 line. So if we record the 0.70, our measurement would be 12.70 millimeters. Now just a reminder, when you do your volume, you need to convert your millimeters to centimeters. So our diameter of this rod, 12.70 millimeters. Let's now do the length of the rod. First put the rod in, hold it tight, find our 0 point, and I will help on this one as well. And it looks like the 0 came between 49 and 50 millimeters, so 49 point something. And then again, we're going to look at the 20 lines. Try to find one that lines up straight across with the other side. And the best fit, sorry for the glare. We'll tip it this way. There we go. I am guessing, I can't get the glare to go away, sorry. There we go. I'm guessing it's the 9.5. That looks like the best, closest one. Yeah, all the other lines seem to miss. So the measurement for this cylinder's length will be 49.95 millimeters. Now, I will do the same and allow you to make your own measurements for cylinder number 2. First, we'll find the 0 line. Alright. And the 0 line looks about the same as the last one. And now we'll look carefully at those 20 lines. Okay. Have you chosen the one that lines up the best? Record that, and you will have your measurement for the diameter of cylinder 2. Let's now do the length. Okay. Clamp the length. We examine where the 0 line lands first. Everybody. Alright. Everybody see the 0 line? Okay, now let's carefully find which of these lines lines up the best. Alright. Everyone, that should be your measurement for cylinder number 2. Let's now do cylinder number 3. Again, first thing, find the 0 point. And then very carefully look at the 20 lines to find the one that lines up the best. Okay, now we will do the length of cylinder number 3. Okay, we have the length. Let's put it into focus, find the 0 line. Okay, and now look at the 20 lines to find your uncertain digits. All right, that finishes the measurement of the diameter and the length, from which you should be able to calculate your volume and your density. On how to use the other method that's going to be used to determine the density of these is volume displacement. The way volume displacement works is if you have some liquid at a certain volume and you add an object without breaking the container, the object will increase the volume proportionally. You will need to record those 2 volumes from the video of the actual experiment. But let's just make a comment about the precision of this particular device. You will notice that every line here is 20, then 21, then 22, and 23. So the certain digits are always the lines. The uncertain digits is the spacing between the lines. And so during the lab, they will demonstrate one time how to estimate between the spaces, and basically in your mind you should kind of divide these up into tenths and say, okay, 50.1, 0.2, 0.3, all the way up to 0.9. And then if your bottom of the meniscus is perfectly on a line, then you get to add a 0. So like if it was perfectly on this line, that would be the 21.0 would be your recording. So again, the point of this lab is, can you obtain correct significant figures or the correct precision in both your measurements, in all your measurements today. Okay, so let's now go to the calculations. And so part 2, let's just make a little comment. We're going to do water displacement for volume. Sorry, I'm writing too fast. And that will conclude the use of these metal cylinders. When we go, all right, we will now use the same 3 metal rods, and we're going to calculate this time the volume by water displacement, or what we call volume by difference. First thing we need is to place a fixed amount of water into a graduate cylinder and record the initial volume. In theory, when you add an object into water, the volume of the object will displace the volume of water equal to its volume. So our first measurement will need to be, what is the volume of the water initially? Let's switch cameras. And we'll bring in this to make it a little darker. And it looks like the volume initially on this one is about 21.3 milliliters. I will help on the first one. So we write that down as our initial volume. Now switching cameras. To add this metal cylinder without breaking the graduate cylinder, we have to very carefully slide it in so that it goes into the bottom like so. And now we can see that the volume has increased, and we just need to precisely measure that. And on this measurement, we'll bring in our black again. We'll turn it so you can see it, and hopefully the glare goes away. But we're almost to 27, just a little under, so we'll record this at 26.8 milliliters. So the difference of those 2 volumes is the volume of metal cylinder 1. We will now do the same thing for metal cylinder 2. I need a voice speaker. Just someplace I can dump the water in when we get the cylinder. Okay. So, that'll work. All right, switching cameras to record our initial volume. This one I will not help you with. So look carefully. It looks like we might need to focus.
Let me pause for a second.
When we go to part 3, we are going to do an unknown liquid density. So we will do density of an unknown liquid. Okay, and we will demonstrate that in lab. Let's erase the W here. Okay. In the liquid densities, we will demonstrate in lab. First, we'll use a graduate cylinder to measure volume, and then do weight by difference. Then we'll use what's called a volumetric pipet to measure the volume, and then also do weight by this difference. So the difference in part 3 and in part 4 is how we measure the volume. This one will have the volume in a graduate cylinder. That's part 3, and the other one will have a volumetric pipette. All right, for part 3 and 4 of today's lab, we're going to take this mystery unknown liquid and determine its density. We're going to, in this case, measure the volume directly using our volume devices, and we're going to measure the mass by difference. So the first thing we must do for part 3 is to weigh an empty graduate cylinder on which we can measure volumes. So record this as the mass of the empty cylinder. Since we're using the empty cylinder for all 3 trials, you can record this one number for all 3 trials. So this is the mass of the empty cylinder. All right, now that we have the mass of the empty cylinder, we're going to add an amount of the unknown liquid and record its volume directly. Get over 20. So we're going to bring this up and put the black notebook behind it and see if we can get this to focus.
You did it for a second.
Actually, we will. Tell me when I'm in focus.
That was good. Right there.
Right there. Okay, very carefully record this volume to the correct precision. We lost focus.
It's okay.
Okay.
It's okay.
All right, now that we know the volume, we are going to weigh the cylinder and the liquid together. Okay, 0 still there. All right, record the mass of this volume in this liquid. Now we're going to add some more of the unknown. And just like before, we're going to record the volume directly.
Put your hand again. And try moving the cylinder around. Try the book again. I'll only get one frame of it in focus, then that's all I need.
Okay.
I can pause it. There. That's about as good as it's going to get.
Let's move back. Come on, go in focus.
Hang on, just wait, there it goes.
There it goes.
It's focused.
Okay, record that volume. Now we will record the mass. Okay, and for our third and final, we'll add a little bit more of the unknown liquid. We'll need to record his volume.
I went into focus for a second up there.
Oh, sorry. There we go. We have it level.
I can manually do it. There we go.
Okay, record the volume. Now we will record the third mass. Now, something you should notice, we will have 3 different volumes with 3 different masses, but when you calculate the densities, they should be nearly identical. Okay. That concludes part 3 of today's experiment. We are now going to take the same unknown liquid and use a different measuring device for the volume. It's called a volumetric pipette. Volumetric pipettes have only one line on them. Can you zoom in?
I can't.
No, not zoom in this. Use this camera. Switch cameras. Okay. And then we'll focus. Now the one line on a volumetric pipette is right there in front of my finger. That is the drainage line that if you use it correctly, this pipette will deliver precisely each and every time 20.00 milliliters. So we're going to use this pipette 3 times to deliver 20.00 milliliters into 3 different containers. So we just have to weigh the containers, and I made them all look different, and record their initial mass before we add the 20.00 milliliters of the unknown liquid. So first, mass number 1. Okay, record mass number 1 in your notebook. Then mass number 2. Record that in your notebook. And then mass number 3. Record that mass in your notebook. All right. Now that we have recorded the 3 masses of the empty container, we need to do the pipetting. And I always like to make sure my pipette bulb actually works. So, the suction hold, this valve has been adjusted and needs to be repaired, so we need a different bulb. I will return shortly. Okay. So let's go to the important part, your calculation of precision and accuracy. And I'm going to do a pretend set of data. Let's say we had a mystery metal X, and somebody told us that the known or the true value was equal to 5.85 grams per cubic centimeter. Now we're going to do all our densities in grams per cubic centimeter because those are the standard units of density in the international system. So 5.85 was the true value. Okay, so we did an experiment, and let's say in experiment part 2 we did 3 trials. So I'm going to call this trial A, trial B, and trial C. All right, I'm going to switch paper now. So give me 1 second. And we'll rewrite. Trial A, trial B, trial C. Okay, so you obtained your height and your length, and if we're doing part 2, we did water displacement and we had a mass, and after we did all the calculations, density of trial 1 came out to be 5.70 grams per cubic centimeter. Density on trial B came out 5.90 grams per cubic centimeter. And density on trial C came out 5.80 grams per cubic centimeter. So that was our final calculated value. Once you have those, you are to do a series of calculations. First thing is to obtain the average. So to attain the average, you guys should know that you sum these up and divide by 3. So we will take and add these together. So you sum by the number of trials and then you divide by how many trials we had. And this one came out 5.80 grams per cubic centimeter. An important note about significant figures: the precision of the average should always be the same as the trials. Should never be less, should never be more. It should be the same as your least precise measurement in your trials. Okay, once we have the average, we are now ready to calculate our accuracy and our precision. Accuracy is calculated by doing what is called the percent error calculation. Percent error is the absolute value of the true value minus your experimental, all divided by the true value times 100%. Okay. Particular case, what did we say the true value was? Previous notes said 5.85. That's needed for accuracy. If you do not know the true value, it's impossible to calculate an accuracy. So I'm going to put in those numbers. Absolute value of 5.85 minus experimental average divided by 5.85 times 100%. Since you are going to do these calculations yourself, make sure you check your math and you can obtain the same on your calculator. So I'm going to do the part in the absolute value first and just make a comment. If perchance your value comes out negative, remember the absolute quantity will make it positive. Mine happened to come out positive, so I don't have to change it. I now done the subtraction. I'm going to now divide that answer by 5.85 and multiply by 100. And I came out with the percent error of 0.854700854701. In your notebook, it's a good technique to always write out the entirety of your calculation. Okay, now the question is, what were the significant figures? Well, in the multiplication division rule, you count the least amount of significant figures, but this has a subtraction. So I'm going to move the subtraction over here because addition subtraction has a separate rule. So when I subtract, I end up with 0.05. Again, addition subtraction is called the precision rule. Your solution can never be more precise than any of the variables. So that means I only have one significant figure when on the top part of this calculation with 3 on the bottom part. So my final answer should be 0.9% error. All right, that is how you calculate your percent error. Let's now do precision. Precision is calculations called the percent average deviation. basically, this is asking is how far did each of the trials deviate. Let's look at them up here. Each of these 3 trials, how far did they deviate from each other and from the average? The calculation is done by taking the sum from 1 to the number of trials of the absolute value of your average minus the experimental value. So you sum up all of those. Then you divide by the number of trials. Then you divide by the average. And you multiply times 100%. Okay, now that looks like a fairly complicated mathematical equation, but we're going to do it in parts. This first part is called the deviations. How far did each trial deviate from the average? And so I'm going to do that first. I'm going to call that the deviations. So in A, trial A, we had an average of 5.80, a trial of 5.70, and if we do the deviation, that was 0.010. So our deviation on A was 0.10. If we do the same calculation for B, we have 5.80 minus 5.890. This comes out negative, but remember absolute values will make it positive, so this one also came out 0.10 for its deviation. And lastly, for C, we had an absolute value of 5.80 minus 5.80, and that came out the deviation 0.00. Okay, that was the calculation inside of the absolute values. Now we're going to do the summation. So to sum your deviations, we just add these 3 together, and you add them together, and that comes out 0.20. Okay, so that was the sum of all our deviations from the average. Now we've done this part of the calculation. We need to average that. That is where we divide by the number of trials. So I'm going to now average. Okay, so this was the sum of the deviations. I'm going to add average in front of this. To average the sum, we take 0.20 and we divide it by 3 trials. Okay, that will give us an average deviation, and I'm going to bring the calculator over. 0.2 divided 3 should be 0.066666 infinity sixes. 0.066666. Okay, so we have now finished down to this step. The next step is to take this average deviation and turn it into a percentage. To do that, you divide by the average and multiply by 100. So we will have our final calculation, which is the percent average deviation, which is our 0.0666 infinity sixes divided by the average, which our average was 5.80 times 100%, and that will give us our thing. So we have the 0.666 in here. We will now divide by the average, which was 5.8, and multiply it times 100, and that will give us a percent of 1.14942528736%. All right, now for significant figures, basically I had 2 back here. I'm going to keep 2 here. So 1.1% was our average deviation. All right, just a comment about rounding errors that students often do. Do not round twice. In other words, do not round the 4 to a 5 and then using the 5 round the 1 to a 2. Make sure you do your calculations correctly. All right, We now have our percent average deviation and our percent error. Let's see if we can, nope, I can't show both at the same time. So, you have several homework questions. It'll ask you, was technique A or technique B more accurate or more precise? The way you determine which technique is more accurate or precise is whichever one has the smallest, for accuracy, the smallest percent error. For precision, the smallest percent deviation. If it was a perfect run, your percent deviation and your percent error would be 0.0. That never happens in reality. And so you will make a determination as to which technique was most accurate and most precise based on these calculations. And that concludes this lecture.